Okay, so now we're going to start with chapter 2, which deals with, as you can see here on the screen, some concepts that you should have met before: atoms, molecules, and ions. You should have met these topics before, of course, in your introductory chemistry. So basically, this is a review for the most part. And as a result, I'm going to go through this rather quickly. All right, so let's start off by discussing a certain laws of chemical combination. And the first law we're going to talk about here is that known as the law of conservation of mass. And if you look in different textbooks, you'll see that they're worded differently. In this case here, it is stated as such: the total mass remains constant during a chemical reaction. In other textbooks or other chemical literature, you'll see something to the effect of, in a chemical reaction, no matter is created nor destroyed, something like that, all right? And basically, it all means the same thing. What it means is that if you have a certain amount of reactant, and then the reaction takes place, and then you get the products, when you weigh the products and weigh the reactants, they'll be the same. That's basically what the law of conservation of mass is all about. And that is very important for what we're going to discuss later on when it comes to stoichiometric calculations. The next law I want to talk about is that of the law of definite proportions. And this law says that if you have a substance, all samples of that substance will have the same composition, all right? Or another way of stating it, all samples will have the same proportions by mass of the elements. So typically when we're talking about the composition of a substance, we're talking about the percentage of each element that is present in the substance by mass, all right? And just to illustrate this example or this particular law, we have this compound known as basic copper carbonate, right? And what you see up here, this bar right here, gives you the breakdown as to the composition of that compound. So the percentage of copper that is present in it is 57.48%. The percentage of carbon is 5.43%. For hydrogen is 0.91%, and for oxygen is 36.18%. And this percentage composition of basic copper carbonate will be the same regardless of where you find this compound, right? So if you find it on the roof of this church building, or if you have a sample somewhere in the lab, it doesn't matter where you get it from. If it's the same compound, then the percentages of the different elements by mass present in that compound will be the same, all right? So that's basically what the law of definite proportions is saying. Okay, so let's look at this example. And this example is talking about the compound magnesium oxide, and it tells you that the mass ratio of oxygen to magnesium in the compound is 0.6583 to 1, right? So basically, for every 1 gram of oxygen, there is 0.6583 grams of magnesium. So the question is asking, what mass of magnesium oxide will form when 2.000 grams of magnesium is completely converted to magnesium oxide by burning in pure oxygen? So down here you see basically how we solve this problem. So the first thing we need to do is find out the mass of oxygen that will react with the 2.000 grams of magnesium. And this is how we set it up. And you'll notice that this conversion factor here is actually representing the ratio that the question gave you between the the oxygen and the magnesium, all right? So that's why I put 0.6583 grams of oxygen above, 1 gram of magnesium below, and then I do the multiplication here. The grams of magnesium will cancel out, so the only unit left would be the grams of oxygen. And when I do the number crunching in my calculator, I end up with 1.317 grams of oxygen. Now, that's not the end of answering the question, because the question is not asking for the mass of oxygen. The question is asking for the mass of magnesium oxide. So therefore, what we need to do is take the mass of the oxygen and add it to the original mass of magnesium, and that will give you the mass of the magnesium oxide. So here we have the final answer, which is equal to 3.317 grams, all right? So that's basically how we do this problem. All right, so let's talk about another law, which is a bit wordy when you look at it. It's called the law of multiple proportions. So I'm just going to read it here and then try to explain exactly what this law is saying. It says, when two or more different compounds of the same two elements are compared, the masses of one element that combine with a fixed mass of the second element are in the ratio of small whole numbers. Okay, so what do we mean by this? If you have two compounds made up of the same elements, but they're two different compounds, for example, carbon monoxide and carbon dioxide, all right? And let's say you choose masses of each of these such that the mass of carbon is the same in both of them. And then you compare the mass of oxygens in those two same compounds. Then what you'll find is that the ratio of the other element in terms of the mass will be a small whole number ratio. As you can see here, in the case of carbon dioxide compared to carbon monoxide, if the mass of carbon is 3 grams in each case, then the ratio of oxygen in carbon dioxide will be twice that in the case of carbon monoxide, all right? So there's going to be a 2-to-1 ratio, as you can see calculated down here. And that, of course, is reflective of the fact that for every molecule of carbon monoxide that is present, compared to one molecule of carbon dioxide that is present, there are 2 oxygen atoms in one molecule of carbon dioxide, whereas there's only 1 molecule of oxygen present in, one atom of oxygen present in 1 molecule of carbon monoxide. So that's where the 2-to-1 ratio comes from, all right? And you'll see this in other compounds as well. In fact, I think the next slide shows you some other compounds of nitrogen, oxides of nitrogen. As stated here, there are 4 different oxides of nitrogen that can be formed by combining 28 grams of nitrogen with 16 grams of oxygen that will form one compound, 48 grams of oxygen will contain or form another compound, 64 grams of oxygen to form a third compound, and then 80 grams of oxygen to form a fourth compound, right? So the compounds that we're talking about here, excuse me, sorry, are these right here, right? N2O, N2O3, N2O4, N2O5, right? And if you were to compare each of these, you'll notice that each of them has 2 molecules of nitrogen, but what is different between them is the number of oxygen atoms per molecule, right? And if you look at the mole ratio, or I should say the mass ratio of the oxygens in each of these cases, where the mass of the nitrogen in each case is the same, the ratio here would be parallel to the ratio of the oxygens when you compare all these 4 compounds, right? So it's going to be a 1 to 3 to 4 to 5 ratio. So 16 to 48 to 64 to 80. If you divide right through by 16, you're going to get 1 to 3 to 4 to 5. All right. So again, this is another demonstration of the law of multiple proportions. Okay. So those are just some laws that we need to talk about before we move on to the next topic, which is Dalton's atomic theory. So this is a theory that was put forward by an Englishman. He was actually a school teacher. His name was, I forgot his first name. Last name Dalton, obviously. And basically what he did was that he looked at all the experimental outcomes, data, whatever, from, his time. And based on his examination, he came up with this idea about, okay, what happens at the microscopic level for different substances in terms of the compounds they form and the reactions that they undergo, right? And of course, it is used to explain, for example, the law of conservation of mass that we discussed, the law of definite proportions, and the law of multiple proportions, all right? So we're going to go through the principal assumptions of this particular theory, the first of which is that matter is composed of atoms, which are tiny, indivisible particles, all right? Now, let me stick a pin here and say that we now know that this is not true. We know that matter is composed of atoms. That part is true. The part that is not true is the fact that, according to this theory, the particles are indivisible. We now know that these particles actually can be broken down into simpler, more fundamental particles, namely the protons, the neutrons, and electrons. And we will talk about that, those different particles later on, all right? The next assumption is that all atoms of a given element are the same. So what this is saying, basically, is that if you can look at one atom of a particular element and compare it to another atom of the same element, they will look identical. You will not be able to make a distinguish between them, all right? The third assumption is that atoms of one element differ from atoms of other elements. So if you take an atom of, let's say, sodium and compare it to an atom of, let's say, carbon, they'll look different if you could actually see them, all right? The fourth assumption is that compounds are formed when atoms of different elements unite in fixed proportions. And this basically explains the law of definite proportions, all right? Basically, when a compound is formed, the amount of elements or the atoms of the elements that come together are in fixed proportions, and therefore that's why the percent compositions of the different elements present in the compound are fixed, regardless of where the compound comes from. The fifth assumption is that when you have a chemical reaction, it involves rearrangement of atoms, right? But no atoms are created, destroyed, or broken apart, all right? And that part, or this particular assumption, explains the law of conservation of mass, right? So the reason why the law of conservation of mass holds true is because the atoms themselves are not created nor destroyed. But basically, when you have a chemical reaction taking place, you have rearrangement of the atoms. So you might have separation of atoms in a particular compound, and then those atoms combine with other atoms to form new substances, all right? Okay, so just to illustrate the theory, Dalton atomic theory, we're going to look at this example here, the reaction between hydrogen and fluorine. Now, let me just write down the equation for this reaction here. I'm just going to squeeze it up here. The equation is H2 plus F2 to give 2HF. All right? So basically, for every one molecule of hydrogen reacting with one molecule of fluorine, 2 molecules of hydrogen fluoride are produced. Now, in this particular example given, you have 2 molecules of hydrogen and you have 3 molecules of fluorine. All right? So basically, what's going to happen is that these 2 molecules of hydrogen will react with these 2 molecules of fluorine. And based on this equation, we can predict that 4 molecules of HF, hydrogen fluoride, will be produced, all right? So that means that this molecule of HF here will be left over unreacted, as you can see here, all right? So basically, as you can see here, and this is based on the the Dalton's atomic theory, you can see how this supports the conservation of mass, because when you take the total number of atoms of the different types on both sides, they're the same. So therefore, the total mass on this side here will be equal to the total mass of atoms on the other side, all right? So basically, that's just basically demonstrating Dalton's atomic theory and how it supports the conservation of mass law. And it also supports the law of definite proportions as well, because as stated here, hydrogen fluoride always has 1 hydrogen atom and 1 fluorine atom, and the proportion is always the same in terms of percentage, 1 to 19 in terms of the mass ratio between the hydrogen and the fluorine. Okay, so let's talk about the subatomic particles. As I said before, we now know that atoms are not indivisible. They can be divided into smaller fundamental particles. And again, this is something you should be familiar with from your previous chemistry experience. We know that we have protons and neutrons that are located at the center of the atom, which is called the nucleus. And then you have the electrons, which are dispersed around the nucleus. And this chart that you see here is basically a summary of the properties of the different particles. So for the proton, this is the symbol that is used. The relative mass of the proton is 1 unit. The relative charge is +1. And as I said before, the proton is located inside the nucleus. As far as the neutron is concerned, this is a symbol that we use to represent the neutron. The mass of the neutron is approximately the same as the mass of the proton. The charge is 0, and inside the nucleus is where that is located as well. And then we have the electrons, which is symbolized by this E- here. And you'll notice that the relative mass of the electron is much lower compared to that of either the proton or neutron. The charge is -1, And of course, the electron is located outside the nucleus. Excuse me. So basically what you'll find is that in any atom, the bulk of the mass of the atom would be the nucleus, which contains the heavier particles, the protons and neutrons, while the bulk, or I should say, most of the volume would be occupied by the electrons, which would be lighter in mass, but they basically surround, or is, as stated here, dispersed around the nucleus. All right? Okay, so let's talk about isotopes. Again, this is something you should have met before, so I'm going to go through this rather briefly. Isotopes are basically atoms that have the same number of protons, but they have different number of neutrons, right? So it's basically possible that you can have an atom of an element that has a certain number of neutrons, and then a different atom of the same element which has a different number of neutrons, but they both have the same number of protons, and that indicates that they both are belonging to the same element. So let's review some definitions here. The atomic number, of course, is by definition the number of protons in the nucleus of an atom, and that number is what is used to identify the element. So each element has its own unique atomic number. And then the mass number is basically the sum of the numbers of protons and neutrons that is present in the nucleus of an atom. And universally, Z is used to represent the atomic number, uppercase Z that is, and uppercase A is the symbol that is used to represent the mass number, all right? And of course, if the atomic number represents the number of protons, and if the mass number represents the sum of the number of protons and neutrons in the atom, then we can easily calculate the number of neutrons by simply finding the difference between the mass number and the atomic number. Okay, now there is a kind of shorthand way of putting all that information together for an isotope. In some textbooks, they call it the isotopic symbol, where it looks like this, where A, the mass number, is written here as a superscript, the atomic number Z is written as a subscript, and then the symbol for the element is simply written like this, where E is, all right? So for example, these are the isotopic symbols for these two chlorine isotopes, right? So this one is the chlorine isotope, which has a mass number of 35. This one is a chlorine isotope that has a mass number of 37. So if you're given something like this, you can tell a lot of things about this particular isotope, right? So for example, you can tell that the number of protons is 17, and since you know that the mass number is 35, that means that the number of neutrons will be 35 minus 17, which will be equal to 18, all right? So that's basically what this tells you, all right? So actually, we answered this question just now. How many protons are in the chlorine 35, which is this right here, 17. And then it says how many protons are there in chlorine 37, also 17, because they're the same element. Let's see, the next question, how many neutrons are in chlorine 37? Well, that's very simple. The difference between 37 minus 17, that gives you 20. Okay, so that's basically what isotopes are all about. So let's see if we can answer this question. How many proton, neutrons, and electrons are present in a bromine 81 atom? Okay, so in this case, it's very simple. The number of protons here, all we have to do is go to the periodic table. Let me see if I can find my periodic table here. Or you know what, let me see if I can locate my periodic table. I should have it here somewhere. Nope. Here it is. So for bromine, in fact, I can just look at this here. 35 is the atomic number. So therefore, the answer to this question is that this is 35. Let me go back to full screen. Okay, so this is 35. This also will be 35 because for any atom, the protons and electron numbers will be the same. And then for neutrons, it's 81 minus 35. 81 minus 35 gives 46. So the number of neutrons present in this particular isotope is 46. All right. So that's a relatively simple example illustrating the relationship between the number of protons, neutrons, and electrons, and the isotopic symbol. All right. Okay, we're going to stop here. And then the next video will deal with the concept of atomic mass. All right.